So we're looking at an example from your homework that you had questions on. We have a function f of x equals 9 over x, and it first wants us to find the equation of the secant line through the points x equals 1 and x equals 9. And so in order to do that, we need to figure out what are those 2 points on the function f of x when x is 1 and when x is 9. And so we can figure that out by going in when x equals 1. We're going to go in here to our original function, and we're going to plug in and look at what is f of 1. So this notation right here, this is just function notation. It's just representing our y value, but it's representing the y value when x is 1. And so we're going to go in here and we're going to plug in. We have 9 all over 1, which is equal to 9. And so we have a point on our function f of x. When x is 1, y is 9. So we want to do the same thing now, and we want to look at it when x is equal to 9. And so when x equals 9, we're looking at f of 9. And this is equal to 9 over 9. Plugging in 9 wherever we see an x. And this is equal to 1. So we have a point here when x is 9, y is 1. We want to find the equation of the secant line. So we need 1 point. Well, we have 2 of them, so we're good there. And we need the slope for when we're trying to find the equation of a line. And so we can find the slope, the change in y. So if I look at this, 9 minus 1, all over, I started with this 9 here, so I need to start with 1 in the denominator, 1 minus 9. So reducing this, 9 minus 1 is 8, all divided by 1 minus 9, which is negative 8. This simplifies to negative 1. So we know our slope is negative 1, and we want to choose one of those points. It doesn't matter which one. It doesn't look like one is easier than the other, so maybe just choose the first one that I have up there, 1, 9. And now we want to find that equation of the line. So I've been doing it in this class where we've been plugging in our value for our point, our slope, into our slope intercept form, and then figuring out what b is. Once we know what b is and the slope is, we have the equation of the line. So my y value here is 9 is equal to my slope, which we said was negative 1, times x, but x in this point is 1, plus b. So we have 9 equals negative 1 plus b. Let's add 1 to both sides of our equation. We get b is equal to 10. So the equation of our secant line is y is equal to our slope, negative 1. Normally I wouldn't put that negative 1 there, right? Times x plus b plus 10. So I'm going to just write it as y equals negative x plus 10. So this is the equation of the secant line through those 2 points. And now part B, they want us to find the equation of the tangent line when x equals 1. So we want to find the equation again at the tangent line, or the line tangent. And so we need the slope and we need a point. We already have the point because we've already done the work from above, 1, 9. And we have to use this point because we want to know when x is 1. And so this is our point when x is 1. So let's look at the instantaneous rate of change, which we found out last week is the same thing as the derivative of the function f of x when x is 1. And we can do that by looking at the limit as h approaches 0. This f of a plus h minus f of a all over h, where a was equal to 1 in this case. So I'm looking at the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. Our function again was 9 over x. So for the first piece, this f of 1 plus h, we're just going in and plugging in this 1 plus h wherever we saw an x and f of x. So let's bring down that limit as h goes to 0 of this 9 over 1 plus h minus f of 1. But recall, we found f of 1 at the beginning. We plugged in 1 where we saw an x and f of x, and we got that that was 9. So we're going to just put, so minus f of 1 is minus 9 all over h. So if we go in here, we do our direct substitution and plug in 0 wherever we see an h, we're going to get that 0. Actually, first we'll get 9 over 1 minus 9, which is 0, all over, plugging in 0 for h here is 0. So we get that indeterminate form. If you have complex fractions and you get this indeterminate form, you want to get rid of the complex fractions. And there are a couple methods to do that. I tend to like to multiply by the fancy one to clear the fractions. And so I look at all the fractions within this main fraction, and I look at my denominators. Well, there's only one fraction in here, so my only denominator I have of the fractions within the fraction is 1 plus h. So I'm going to multiply the numerator by that common denominator, which is the only denominator in there, 1 plus h, and the denominator by that 1 plus h. And the whole point of that is when we distribute, our fractions will clear out. And so again, let's bring down our limit as h goes to 0. I have this 9 all over 1 plus h. I distribute this. So this is all times 1 plus h minus 9. I have to distribute to the other grouping in the numerator. So all times 1 plus h divided by this h all times this 1 plus h. So fraction cancels in the numerator, and you're just left with 9 for that first piece. So we have 9 minus, maybe we can distribute now. Let's distribute this negative 9 inside the parentheses here. So we have negative 9 times 1. So minus 9, and then negative 9 times h minus 9h. All over. And I'm not going to distribute on the denominator because the whole point is that if I don't distribute, then we're going to have like factors that we can cancel. Okay, so 9 minus 9 in the numerator simplifies, those go away, cancel out. Oops. This should have been h equals 0. Somehow it turned into a 9. And so we have negative 9h all over h times 1 plus h. So notice we have those h's cancel. And so now we can take the limit. When we go in and plug in 0 wherever we see an h, it's not going to give us an indeterminate form. So we have the limit as h approaches 0 of negative 9 all over 1 plus h. So do direct substitution. And we get, this is equal to negative 9 all over 1 plus 0. So negative 9 over 1, which is negative 9. So the instantaneous rate of change when x is 1, so the slope of the function f of x equals 9 over x when x is 1 is equal to negative 9. So we have the slope of the tangent line when x is 1. And we have the point on the tangent line when x was 1, y was, I believe, 9 here. And so now having the slope and a point, we can find that equation of the line. You can do point slope formula or do what I've been doing, using your slope-intercept form. Plug in your point. So plugging in 9 for y is equal to your slope, which in this case was -9, times x. So x when y was 9 is 1, plus b. So I have 9 equals -9 plus b. Let's add 9 to both sides. And this is b is equal to 18. So now because I have b, I had the slope of the tangent line, we have the equation of the tangent line. Y is equal to our slope, -9 times x plus b, so plus 18. So questions on that? So almost identical to what we were just doing. This time though, we have a function. It's y equals 9 square roots of x. I'm gonna change that. Instead of y, I'm gonna call this f of x. So we have f of x is equal to 9 times the square root of x. We wanna find the equation of the tangent line to the curve when x has the first value. So when x is 25. And so we need to find out what the point is when x is 25 on this function. And so we're going to go in and we're going to plug in 25 wherever we see an x in the function. So this is just the y value when x is 25. That's all this f of 25 is saying, is equal to 9 times the square root of 25. So simplifying, 9 times square root of 25 is 5. So 9 times 5 is 45. And so we have a point at 25, 45. Okay, so we have a point on the line. Now we need to find the slope, the instantaneous rate of change on that function, y equals 9 times the square root of x when x is 25. And so we're looking again at the limit as h goes to 0. Of that f of a plus h, but a in our case, remember, is 25. So let's just do that right now. So the square root of 25, oops, 9 in front, 9 times the square root of 25 plus h minus f of 25, but we just found what that was, right? We just found that that was 45, so minus 45 all over h. So just using the definition for the instantaneous rate of change at a particular value of x. So if I go in here again and I plug in 0 wherever I see an h, well, that would give me 9 times the square root of 25 on top, which is 9 times 5, 45, minus this 45, which is 0, all over 0. So we get that indeterminate form, and that doesn't tell us anything. So we got to go back and manipulate it. And so if you have radicals in here, irrational functions with radicals, and you're getting 0 over 0, you're going to want to multiply by the conjugate, the terms with the radical. And so before we do that, just so we don't have to have such big numbers, I'm going to actually notice the numerator has a 9 in common. We have a 9 and a 45. They both are divisible by 9. We know we can pull that constant out front, and that might help us just so we don't have to deal with such big numbers. So maybe let's do that first. So basically, they both have a 9 in common. I'm just going to pull the 9 in front of my limit, and I know I can do that by limit rules. So I can pull this 9 in front all times this limit as h goes to 0. If I factor out a 9 in the numerator, that's left with a square root of 25 plus h minus, factoring out a 9 from this 45, I'm just left with 5 all over h. So multiplying by that conjugate now is square root of 25 plus h underneath the radical. Change the sign in between the groupings. So this is now going to be a plus. 5. All over, we're multiplying by 1, and we can only multiply by 1, so we couldn't just do it to the numerator. We have to do it both to the numerator and denominator. And that's a difference of squares. So 9 times the limit as h goes to 0. So this is squaring the square root of 25 plus h minus 5 quantity squared, all over h times, and I'm just going to leave it in factored form, 25 plus h plus 5. So if you square a square root, the square root falls away, and we are just left with a radicand. That's just what's underneath the radical. And so I have 9 times the limit as h goes to 0. And squaring the square root, we get 25 minus h minus, and then squaring this 5, we get 25 all over h times that quantity square root of 25 plus h. And then outside of the radical plus 5. So notice in our numerator, those 25s cancel out. I have a 25 minus a 25 up there. And I'm just left with a negative h then, all over h, square root 25 plus h plus 5. So notice our h's cancel in the numerator denominator. And we're left with 9 times the limit as h goes to 0 of negative 1 in the numerator, all over the square root of 25 plus h plus 5. So now we can go in and do our direct substitution. And we're going to get a number back. So don't forget about that 9 we factored out. So we have 9 times this negative 1 all over square root of 25 plus 5. So 9 times negative 1 all over, well, square root of 25 is 5. And then I have this 5 plus this 5, which is 10. So I get that my slope of my tangent line is negative 9/10. So I have the slope of the line, and I have a point on the line. So I should be able to find the equation of that tangent line. So now looking at this equation of the tangent line, we have y equals mx plus b. Let's plug in our point and our slope. And so x was 25, y was 45. So we have 45 equals our slope, negative 9/10, times x, which is 25 plus b. So before I isolate b on one side, I notice I can simplify this negative 9/10 times 25. I have a 5 in common in the numerator and denominator. So this would reduce. So we have 45 equals negative 9 times 5, so negative 45 all over 2 plus b. So when we get this on the other side, when I add 45 halves on the other side, I'm going to need a common denominator. So let's do that. Let's multiply. Our denominator for those terms are going to be 2, so 2 over 2. So this would give me 90 halves. And then adding 45 halves equals b. So 90 plus 45, that's 135 halves equals b. So we know what b is, we know what the slope is, and so we have the equation of the tangent line. Y equals negative 9/10 times x plus b, which was 135 all over 2. there's the equation of the tangent line of that function, 9 times the square root of x at x equals 25.